Okay, so let's start with an example. Example 1, hypothesis test for a population mean, where we assume the population standard deviation is unknown. All right, a large class takes an exam. Assume that the scores are approximately normally distributed, which means what theorem applies? CLT, or the variation we need for the t-distribution. We randomly sample 7 exams, and it's good to know what these pieces are. What's the 7? It's n, our sample size. The sample mean, what's the notation for sample mean, by the way? It's x bar, all right? The x bar is, x bar is 67.5 points. Put that over here. It's good to indicate these things so you don't have to keep rereading the problem over and over again. The sample standard deviation is 3.2 points. 3.2 points. That's S. If we're assuming that we don't know the population standard dev, we better at least have the sample standard dev. Test the claim that the average exam score for the class is less than 70.0 points at the 0.05 significance level. Now, before we go on, imagine this scenario. So I'm a professor of a large lecture hall class with 1,000 students. I look around, and I see that they're sweating. They're sweating, they're nervous, they're cursing under their breaths, right? And I turn to my TA, Igor. Igor is my longtime TA. And I tell Igor, you know what, Igor? I don't know if these people are going to pass this exam. I'm not going to curve the grades. It's out of 100 points. I don't know if these people are going to pass the exam. So I tell Igor, I'd like for you to grade some exams. After the exams are turned in tonight, for an hour tonight, I'd like you to grade 7 of these exams randomly, random sample of 7 exams. Do a statistical analysis on that sample, and tell me tell me what to do about my claim that the average exam for the class is less than 70 points, because I don't think these people are going to pass. I'm claiming to you, Igor, that these people overall are not passing the exam. I think that I think the average exam score is less than 70 points. That's what I claim to you, Igor. Test that claim based on your sample tonight. So Igor, at the end of the exam, Igor grabs he says, yes, master, to me. And he says, he takes the stack of exams, all right, throws them up in the air, and randomly grabs 7 of them as I hide under my desk. Probably better to use a random number generator. He grades the 7 exams, does some basic data entry on Excel, and finds that the sample mean for the 7 tests is 67.5 points, and the sample standard dev is 3.2 points. We saw how to do that in the first part of the course. All right. Oh, and the 0.05 significance level, remember? Fishy, alpha. Okay. Rounding instructions vary, but here we're going to round off to 5 sig figs or sig digs, except we're going to round off the t-test statistic to 3 decimal places. If you round off to 5 sig figs, you should be good in our class. Okay, so we're going to need these hints about the t-distribution on 6 degrees of freedom. Remember, if the sample size is 7, then the number of degrees of freedom we're going to need will be 6. And I'm not going to trick you on this. I'm not going to say, oh, I tricked you. I gave you the wrong number of degrees of freedom here, so no credit. No, I'm not going to pull a stunt like that on you. This will be correct. All right. Now, this picture also hints at something here, but I'll get to that later. Solution. So let mu be the population mean exam score for the class. It's good to officially state that somehow, or perhaps you could label that over here. Average exam score for the class, that's mu. Good to indicate what mu is. We should write it out. Okay, the methods of this lesson apply because, well, we're doing a test for mu. We're assuming sigma, the population standard dev, is unknown. So it's going to be a t test, not a z test. And we're also going to assume that and because we're assuming that the exam scores are about normally distributed, then the CLT applies. So we can use the procedures of this lesson. Remember, here we assumed a normal distribution overall for the class, the 1,000 students. Okay. Now, bear in mind, I'm not going to trick you here, but be aware of these things, right? And it's going to be a t-test, not a z-test. Here is the setup for this. It's going to be a left tail test, and we'll see why. Now, take a look at the claim. The average exam score for the class, mu, is less than 70 points. Is less than 70 points. So the claim corresponds to this over here. Now, this says that mu is less than 70 points, which is our reference point, 70 points. Now, since this does not include the case of equality, the claim here turns out to be the alternative. Which means, in this test for mu, here's a mu number line, which means that the alternative here favors lesser values for mu, smaller values for mu. So if the population mean really is 60 points or 50 points, we're in here. Remember, and so it's a left tail test. Remember, the type of test, in the sense of it being a two-tailed test, a left-tailed test, or a right-tailed test, that depends where the alternative is pointing. Here, the alternative points towards lesser values of mu. So kind of corresponding to a left tail. By the way, hint, hint, the picture here hints that. And again, I'm not going to try to trick you on the picture, right? Now, I might have a multi-part problem where I have various pictures, but I'm not going to try to intentionally trick you here. Take a look. I'm giving you a left tail probability. Hint, hint. That's okay. That's a hint. All right. Now, the null hypothesis would technically say, that mu is greater than or equal to 70 points, all right, the reference point. But again, remember that it is conventional for us to replace this symbol with is equal to. You're welcome. In part because we're going to base calculations on the notion that the null is true. In this case, that the mean mu is exactly 70.0 points. Although this does in fact wrap in other cases. This is the boundary case for this here. And we're going to assume for now, as we perform our calculations, that mu is 70 points. Again, it's like assuming a coin is fair, right? When we were testing for P. It's like assuming a coin is fair. Under the assumption of a fair coin, we're able to work out probabilities and do all sorts of calculations. Here, if we assume that mu is 70 points, then we know the distribution for X bar. Assuming that we trust our value for S. Assuming that S does a good job of estimating sigma. The sample standard dev does a good job of estimating the population mean. Fishy. Alpha, the significance level, is 0.05. So it's not as lenient as a 1% judge. It's more lenient than a 10% judge. All right. In terms of rejecting the null, remember, here's alpha. We reject the null if the p-value is less than alpha. All right. So the lower alpha is, the harder it is to reject the null. And we give David more of a pass. Here, kind of in the middle, standard. We now identify the sample statistics. Okay, the sample size, which should have been really predetermined. The sample size n equals 7 exams. I told Igor, I want you to grade 7 exams tonight. And then early in the morning the next day, I'll look at your results. We want to use the t-distribution on, well, if n is 7, n minus 1 is 6. We want to use the t-distribution on 6 degrees of freedom. As we just identified, it was helpful that we labeled these. So when Igor grades the 7 exams and goes into Excel, Igor finds that the sample mean, X bar, is 67.5 points. The sample standard dev S is 3.2 points. Again, it helps to do some labeling along the way so that you don't have to completely reread the problem. Personally, I always hated doing that on standardized tests. It's good to indicate things, kind of indicate the notations, right? Makes it easier. I mean, these word problems, they can be easy to parse. I mean, it's not like an SAT word problem. You can actually break this down into very digestible pieces. Do it. Okay, so sample mean X bar is 67.5 points. Sample standard dev is 3.2 points. And we really need this because, again, we're not assuming that we know sigma, the population standard dev. We need at least the sample standard dev, S. And we're going to use a t-test statistic right here. We now compute the t-test statistic. That formula I showed you, right? Based on the central limit theorem and the fact that we're using S to approximate sigma. Remember, the fact that we're using S to approximate sigma, that's why we're using a T, not a Z. All right, here's the formula. The sample mean, X bar, the sample mean that Igor actually got from the 7 tests, his Excel worksheet, 67.5 points. Minus, now remember, we're plugging in the value for mu under the what? Under the null. Okay, under the null. The null says mu equals 70 points. So this is under the null. This here, the 67.5, that's based on our sample. From sample. It's a sample mean from our sample. Sample mean minus the hypothesized value for the mean under the null, all over S, the sample standard deviation, 3.2, over the square root of n is 7. On your calculator, you might want to work out the numerator and the denominator separately to avoid confusion. Otherwise, you might have to use a bunch of grouping symbols, right? Remember, if you were to put this all in on a calculator, you'd want to put this top, the numerator, in parentheses, and this bottom, the denominator, in parentheses. Again, I might suggest calculating the top and the bottom separately. And we're going to 5 sig figs. My recommendation here, all right, round out to 5 sig figs or sig digs. In the middle, round out the t-test statistic to 3 decimal places. Okay, so over here, when you do this, it turns out you'll get negative 2.067 as your test statistic for t. So this is, okay, the t-test statistic that tells us about our sample and how it relates to the null. If the null is true, how unusual is our sample results? If the mean for the class for all 1,000 students when Igor is done with the grading for the entire class, right? If the population mean does in fact turn out to be 70 points, okay? How unusual would this test statistic have been? Oh, now many of you might go, oh gosh, I think it's going to be so easy for me to fumble on my calculator. I understand. But remember, Hints can help. Hints can help. I'm not trying to be hard on you folks. Hints can help. I'm not lying to you. Hints can help. But you do have to show work, okay? I mean, don't just use the hints. I don't want you to just use the hints. You have to show me the work. You must show me this. You must show me this. On homework or any exams, you must show this. Bear in mind, you don't have to write this out if you write this out. I would recommend writing both. And write all this. I do recommend you write all of this. All right. Now, okay, so this t-test statistic, again, is a measure of how unusual, right? It will help us measure. Well, it's a metric. It will help tell us how unusual our sample results are. Okay, assuming that the population mean is in fact 70 points. A p-value would help. We now find the corresponding p-value. A probability will attach to the sample. This p-value will tell us what's the probability of getting at least as unusual a sample. I'll write this out, then I'll type it out. It's been a while. P-value. What is the probability that, I'm going to need a smaller font. What is the probability that we get sample results at least as unusual as what we got, namely that X bar, the sample mean, was 67.5 points. That was that number up here, remember? Okay. What is the probability that we get sample results at least as unusual as what we got if the null were true, assuming that the population mean is 70 points? So if the population mean were in fact 70 points, what's the probability that we get something as unusual as 67.5 points as a sample mean for a sample of 7 tests? All right. And the idea is that if this p-value is really low, if it's kind of like if the null is saying the coin is fair, we flip the coin 100 times, and we get 10 heads on 100 flips. 10 heads on 100 flips. What's the probability of getting something at least as unusual as that if the coin were in fact fair? Well, if you're getting 10 heads in 100 flips, you're going to have a very low p-value, right? It's very unlikely you're going to get something as extreme, something at least as extreme as 10 heads, whether it's one-tailed or two-tailed for that matter, if the null were in fact true, okay? Likewise, if the mu were in fact 70 points, right? Well, what's the probability of getting something at least as extreme as this kind of a t-test value if the null were in fact true? This is what we're getting from our sample, okay? And what's the deal? Either our sample is really unusual or the mean was false. And so since we're taking a random sample, right, we're assuming that we're taking a simple random sample, there's no reason for any inherent bias. So if we have to choose between, if we have to choose between the sample was really, really, really unusual just by pure chance. Oh, we just happened to get 10 heads on 100 flips from a fair coin. It was a fair coin, but we just got really, really, really unlucky with the heads. If there's a choice between that, right? Null is true, but we just got really, in a way, unlucky, maybe. Or are we going to determine that the null was messed up to begin with. The null was basically wrong. So again, if we flip a fair coin, okay, if we were to assume that the coin were fair, right, and we got 10 heads and 100 flips, so what are we inclined to think? Are we going to be inclined to think, wow, it's just a heavy tail day. It's just one of those days where it's a whole lot of tails. But I really think it's a fair coin. Are you going to think that, or are you going to think there's something up with this coin? It's a biased coin. Well, we're probably going to think it's a biased coin. Okay. So likewise over here. Okay. If this is too ridiculous, then we're going to say, there's no reason to think it's a biased sample. You know what? We're going to dump this null. Anyway, we now find the corresponding p-value. It's a left-tail test, so we need a left-tail p-value. All right. Use the hints. Our test T was negative 2.067. It turns out that the left tail probability for this left tail test was 0.0421. I'm not going to be mean and give you the right tail just to be mean, although I may have a multi-part problem with multiple hints. But the p-value, the left tail p-value is 0.0421, about 4%. All right, 0.0421. Let's compare that to alpha, our significance level. This is the p-value. Is the p-value low or not low? Is it less than alpha or greater than alpha? That's about 4%. This is 5%. It's a bit close, but the p-value is less than alpha. In that sense, the p-value is low. The p-value is low. Remember the rhyme. If the p-value is low, the null must go away. What do we do with the null? What's our decision? We reject the null. That's our decision. The decision desk on election night. Null loses. We reject the null. Finally, we write our conclusion relative to the claim. All right. We reject the null. Is that a strong result or a weak result? It's a strong result. That's a strong result. So there is sufficient evidence, not insufficient evidence. There is sufficient evidence of what? Well, what was the claim? The claim, remember, was the alternative, that the mean was less than 70 points. I looked around, I saw the sweating, cursing students, and I said, these people aren't passing. These people aren't passing, for the most part. Maybe Igor's brother is passing, because Igor's the TA. No. All right. The alternative is the claim. So it's like the research hypothesis. Hey, I'm a professor. I do research, right? I don't, but all right. The alternative is the claim. Can we prove the research hypothesis? We're weighing evidence for the claim. We're weighing evidence for the claim that the average, see the claim's right here, that the average exam for the class, mu, is less than 70 points. So conclusion, the final conclusion, what we tell, well, I do know statistics, but Igor still wants to give me the layperson's final conclusion. We should write complete sentences at the end. This is, especially nowadays, in these days of Common Core. Right? Final conclusion, there is sufficient evidence for or in support of the claim that, what was the claim? You might even want, if you're rushing on an exam, you might even want to star the claim. Let's put this in red. The claim is that the average exam score for the class is less than 70 points. That's all the claim star. There is sufficient evidence for or in support of the claim that star, the average exam score for the class is less than 70 points. So remember the overall context. And we are done. Yeah, okay. Remember the overall context. I'm the professor. I am the professor. I look around. I see my students sweating and cursing on the exam. All right. I turn to Igor, my TA. I say, Igor, I don't think these people are passing for the most part, and I'm not going to curve the scores or grades. I think the average exam score, the population mean for the class, will be less than 70 points. I claim that mu is less than 70 points. So again, Igor takes his random sample, grades the exams, does the Excel thing, finds the sample statistics. We knew n was 7. Well, let's say I tell Igor, randomly grade 7 exams tonight. I tell you the sample size, randomly grade 7 exams tonight. Igor says, yes, master, I will do that, because Igor does everything I tell him to. Yeah, he's going to wash my car this weekend, if I needed a car, really. I mean, all right. Okay. And okay, so I see the sweating students. Igor gets these sample statistics. Okay, we run the hypothesis test. So even though I think that the students didn't pass, for the purposes of calculation, we're going to assume that mu was exactly 70 points. This is for the sake of argument, okay? So it's like a fair coin. If the mean were in fact 70 points, okay, that's like the borderline case, right? The population mean could have been 71, 72, 73, but we're going to take the borderline case, 70 points, okay, as our hypothesized assumed value. So under that assumed reference value from you, 70 points, how unusual is this sample? How unusual is this sample, given that we got these sample statistics under n equals 7? Given that we got these sample statistics, how unusual was our sample? Well, let's say that the population mean were in fact 70 points or higher. Let's just say, in fact, overall, on average, the pass is passing. Basically, we want to ask, so the fact that Igor's sample, the 7 tests that Igor randomly selected, okay, well, what's the deal? Again, how unusual would that sample be? Given that the sample mean were 67.5 points, the sample mean is a bit on the low side, right? If the population mean were in fact 70 points, then this would be a bit on the low side. So we want to know, well, if we're still assuming the 70 point, that the mean, the population mean, mu, is 70 points, well, how unusual would this have been, right? Could this be chalked up to sampling error? Basically, if we're assuming the null is true and we see something like this, we're asking, well, can we chalk it up to sampling error? I shouldn't have done that. Is the discrepancy from 70 points, the difference from 70 points, can we chalk that up to simple sampling error? Or, no, the sample is just too messed up, too unusual. Reject the null. Reject the 70 points. Okay. So the sample mean was 67.5 points. It's a bit low, right? How unusual would the sample be? The t-test statistic is negative 2.067. That may not mean much to you. Okay, so let's find the p-value. It's a left-tail test. The probability of getting, if the mean were in fact 70 points, and see the thing is, if Igor had gotten a sample mean of 70 points, the t-test statistic would have been 0, all right? But yeah, the sample mean that Igor got, 67.5 points, was a bit low, okay, and the t-test statistic is negative. The probability of getting something that's as low as this or lower than that just by chance, like with the coin, if you assume a fair coin and you flip the coin 100 times, okay, if it were a fair coin, how unusual would it be to get 10 heads or lower? Likewise here, if the true mean were in fact 70 points, okay, how unusual would it be that just run a random sample, we get a sample of 7 tests with a t-score of this or lower? It's about 4%. Is that low? Yes, it's lower than alpha. It's too low. It's just too low. So we reject the null. So it's like getting 10 heads. This really is like the situation where it's like 10 heads. The left tail probability is just too low. All right. Which means that if we have to choose between, oh, well, the mean was in fact 70 points. This sample just got really unlucky. Or, it's too unusual. The null was wrong. The coin was not fair. We're going to go with the null was wrong. The coin was not fair. The mean was not 70 points. There is sufficient evidence for my claim that the average exam score for the class was less than 70 points. So when I told Igor, I don't think this class is passing. All right, I think they're failed the exam, basically. Well, based on this hypothesis test, because of Igor's sample and this test, we now have, even that night after Igor grades the 7 exams, he doesn't have to grade all 1,000. Then we have a census. That night when Igor grades the 7 exams, all right, and then I wake up at noon, all right, and I ask Igor, what's the deal, right? Igor says, Master, there was sufficient evidence for your claim because you're so awesome. There is sufficient evidence for your claim. You were right last night. You were right that that class is not going to pass. And then when Igor grades the 1,000 exams, it's likely that will be the case. When the 1,000 exams are entered, their scores, Igor finds the true population mean. It's highly likely that the mean is going to be less than 70 points. All right. Next time, we've been doing the p-value method. We're going to look next time at the traditional or classical method for hypothesis testing.